Hi everyone, this is Mrs. G, and today we're going to be graphing rational functions. First, please pause the video and give this warm-up a try. All right, go ahead and check your work here. This should be our final answer. So remember, once we complete our long division, this is our quotient, and then this is our remainder. So we will write the quotient plus the remainder over the divisor. So the reason why we're reviewing long division at this point in the year is because that's going to be one of the tools that we use today to help us graph different forms of rational functions. So look at this new form of a rational function. Here we have 3x plus 5 over x plus 1. In the last lesson, we learned how to graph rational functions in this transformational form, a over x minus h plus k. And from this form, it was really easy for us to identify the vertical asymptote and the horizontal asymptote. So when we have something in this form, one strategy we can use is we can use long division to rewrite it in this transformational form. So let's give that one a try. So we're going to do 3x plus 5 divided by x plus 1. So 3x divided by x is 3. We multiply and we subtract. So this leaves us with 3 plus 2 over x plus 1. Now, if you simply flip the order of those two, you don't have to do this, but just to really make it match, to drive home that this is just transformational form, we could say 2 over x plus 1 plus 3. So from this form, we should know what to do. We do have a vertical stretch by a factor of 2. I'll write out the transformations. Vertical stretch by a factor of 2. And then we have that horizontal translation left 1, which will also shift our asymptote to the left 1. So I'm going to sketch in that vertical asymptote at x equals -1. And then we also have a vertical translation up 3, the plus 3 at the end. And remember, originally our parent function has a horizontal asymptote at y equals 0, so that will get shifted up to y equals 3. So you can sketch that in as well. And then from here, we're simply going to pick maybe a point or two to the right and left of our vertical asymptote, so we get a better idea of what our graph looks like. So I'll do 0 first. So if I do f of 0, I'm going to plug it in here. We have 2 over 1, which is 2 plus 3, which is 5. So we have the coordinate 0, 5. I'll also plug in f of 1. That's a pretty nice number to plug in because we get 2 over 2, which is 1, plus 3, which is 4. So on the right side, our graph is going to do something like this. It's going to travel along our asymptotes, and we can guess that the other piece of our graph should be down here, but we'll still get some exact coordinates for the left side of our graph. So let's plug in -2. So if I plug in -2, I have 2 divided by -1, so -2 plus 3 is 1. And we could also plug in -3, which will give us 2 over -2, which is -1, plus 3 is 2. And then we're going to travel along the asymptotes while going through the coordinates, and we are done. So again, we can still use the strategies that we learned in the last lesson to graph something in this form. We simply just have to do a quick little round of long division first to rewrite it in that form. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So check your long division. It should give us 1 over x plus 2 plus 2. So this left 2 will shift our vertical asymptote to x equals -2. And then this plus 2 will shift our horizontal asymptote to y equals 2. And I plugged in a coordinate or an x value to the right and left, and I see that I have a graph that looks like this. Now let's say we don't want to rewrite our equation in transformational form. It is very possible to graph from this form. So when we have a rational function in the form of ax plus b over cx plus d, there's two things that we really need to find, and those would be the asymptotes. So you can find the vertical asymptote by simply taking your denominator and setting it equal to 0. So a vertical asymptote is actually a domain restriction. It is what your x value cannot be. Notice that your graph doesn't touch it or cross it, and we know that a denominator cannot be 0. So if you figure out where your denominator is 0, you know that you will have a vertical asymptote there. So that's how you can find your vertical asymptote. Pretty easy to do. And the horizontal asymptote is even easier. When it's in this form, you simply look at the ratio of the leading coefficients. So the leading coefficient of the numerator is a, the leading coefficient of the denominator is c. It's whatever a over c is, and that's going to be your horizontal asymptote. So that one you can tell just by looking at it. And then just like we've been doing, we're going to plug in values to the left and right of the vertical asymptote to graph. All right, let's give this one a try together. So the first thing I need to do is identify my asymptote equations. So let's start with the vertical asymptote. So remember, the vertical asymptote we find by taking our denominator and setting it equal to 0. We're looking for the place where our function is undefined. And again, that will always be where our function has a denominator equal to 0. So if I solve, I get x equals 3. So that's actually going to be the vertical asymptote equation. Now I need to find the horizontal asymptote equation. Remember, for that, it's always going to be the ratio of the leading coefficients. So the leading coefficient of the numerator is 2. The leading coefficient of the denominator is 1. If you don't see a coefficient, it's a 1. So it's just the ratio of those, so 2 over 1. So y equals 2 over 1, which is just y equals 2. So those are the asymptote equations. I'm going to sketch those in to give a guideline for the shape and behavior of my graph. Then we just need to find a couple of exact points to the right and left of the vertical asymptote. So let's try f of 4. So we have 2 times 4 plus 1 over 4 minus 3, which is 9 over 1. So we have the coordinate 4, 9. All right, let's find one more coordinate to the right. Let's do f of 5. So here I have 2 times 5, which is 10, plus 1 is 11 over 2. So I'm just going to have to estimate where this is in our graph. But we know that it should be between 5 and 6 for the y value. So 5, and then somewhere around here. And we also know, again, the general shape of our graph. We know it's going to travel along the asymptotes. So with just a couple coordinates, we can actually sketch in a pretty good graph. Now we do need some coordinates to the left of the vertical asymptote. Let's do f of 2. So we have 2 times 2 plus 1 over 2 minus 3. So we have 5 over negative 1. So 2, negative 5. And let's do one more. Let's do f of 1. So 2 times 1 plus 1 over 1 minus 3. So that gives us 3 over negative 2. So 1, negative 3 halves. So between negative 1 and negative 2. And then again from here, we know what the general shape will be. So we'll just travel along the asymptotes and we will be good to go. All right, so now let's talk about the domain and range of this function. So we can see for the domain, our graph is going to touch every single x value except for the vertical asymptote. So if I want to write this in inequality notation, we could actually use that all real numbers symbol. Remember, this means all real numbers. And then we can actually write except x equals 3. So that's one way we can write it. Now using interval notation, this one's going to be a little different because we have that exception in the middle. So this is going to look a little strange, but it's good to practice. So I start with my left boundary, which would be negative infinity, and then I know that it's going to keep going up until 3. So I do negative infinity to 3, but I don't want to include 3, but then I see that it starts again at 3 and then it goes to infinity. So I'm going to do a union symbol, which means or. So it's negative infinity to 3 or 3 to infinity. And because we have parentheses here, this is saying every number except for 3. So I know it looks a little bit strange, but this is how we would write this in interval notation. Now for the range, it's going to look similar. Look at my y values. It's going to hit everything except for 2. And then after 2, it hits every y value again. So the range is going to be all real numbers except for y equals 2. And in interval notation, again, I go negative infinity to 2, not inclusive, or with a union symbol, and then I pick back up again, and then I go 2 to infinity. But again, because 2 is not inclusive, this is essentially saying all real numbers except for 2. So there you go. Here we have our domain and range in 2 different notations. Okay, let's try one more together. So again, we need to start by identifying our asymptote equations. So let's start with our vertical asymptote, and we find that by taking the denominator and setting it equal to 0, which again will give us a domain restriction. It's the one x value that x cannot be because it's when our denominator is 0. And then for the horizontal asymptote, it's going to be the ratio of the leading coefficients. In this case, that's just going to be 1 over 1. So y equals 1. All right, I'm going to sketch those really quick. So x equals negative 3. Y equals 1. Make sure you're always using dotted lines for this. And then let's find a couple additional points. So let's plug in maybe negative 2. So we have negative 2 minus 1 over negative 2 plus 3, which gives me negative 3 over 1. So I have the coordinate negative 2, negative 3. Let's find f of negative 1. So we have negative 1 minus 1 over negative 1 plus 3, which gives us negative 2 over 2. So that's negative 1, negative 1. And I can connect my dots and travel along the asymptotes. Let me label those really quick. I forgot to do that. Okay, let's do a couple points to the left of the vertical asymptote. So negative 4 minus 1 over negative 4 plus 3 would be negative 5 over negative 1. So we have the coordinate negative 4, positive 5. All right, last one, let's do f of negative 5. So negative 5 minus 1 over negative 5 plus 3. negative 6 over negative 2 gives us the coordinate negative 5, positive 3. And again, I know that my graph is going to just travel along the asymptotes. I'm going to kind of extend it off my axis, but that's okay. We can go a little bit off for this example. So it will look something like this. Again, our domain is always going to be all real numbers except for the vertical asymptote. So all real numbers, I'll do the R symbol with the extra vertical line, except x equals negative 3, or we could say negative infinity to negative 3, non-inclusive, union, so or negative 3 to infinity. So that's a way of saying negative infinity to infinity, but leaving out negative 3. And our range is always going to be all real numbers except y equals 1, at least for our basic functions. And we could also say negative infinity to 1 or 1 to infinity. There you go. All right, here's one last example for you to try on your own. Please pause the video and hit play when you're ready to check. All right, go ahead and check your work here. Check that you have a vertical asymptote at x equals negative 2, a horizontal asymptote at y equals 3. Here you can see my work for how I found these 4 exact coordinates, and then you can see that my graph travels along the asymptotes in the opposite quadrants. And then also check your domain and range. Domain is everything except for negative 2, and the range is all real numbers except for 3. All right, that's all for today's video. Thank you so much for watching.